Welcome to your podcast for Lesson 39, Multiple Objects and Internal Forces. After viewing the podcast, you should be able to isolate an individual object located within a system and draw all the forces acting on it, and also to use Newton's third law to identify all of the internal forces of a system that consists of multiple objects. So for the warm-up activity, and we'll draw this on the next screen, we're going to have a 1 kilogram block at rest on top of a 5 kilogram wood block. What is the weight of each block, and then what is the normal force acting on each block, and then draw a diagram of this system. So in this series of lessons, we're going to be looking at systems, which are used to describe the interaction of forces between multiple objects. So we're going to be using the same formulas that we did throughout the beginning of the year. It's just rather than just a single object that we're looking at, now we're looking at more than one object within this system. So from our warm-up activity, you can see we have a 1 kilogram block sitting on top of a 5 kilogram block. Okay, we were asked to do two things. We were asked, first of all, to find the weight of each block, and second of all, to find the normal force acting on each block. So we're going to start off with the easier of the two, which is block number 1. Okay? When we look at block number 1, we see, of course, it's sitting on top of block number 2. We know it has a mass of 1 kilogram, and we learned in the last series of lessons that we're going to calculate an object's weight by using m times g, or its mass times our value of 10 for gravity. And so we know that box number 1 is going to have an FW which acts straight down, and m times g, 1 times 10, it's going to have a weight of 10 newtons. Now, in the last couple lessons, this would have been sitting directly on the table, and we know that the table would be providing a normal force that acts perpendicular to that contact surface. Here, it's not sitting on the table, but it is making contact with block number 2, which in this case will provide that normal force, which is still going to be perpendicular to that contact surface. And because we know that F net has to be 0 here because block 1 is at rest on top of block 2, I know that it has to be equal and opposite of FW. So its normal force is also 10 newtons. When we look at block 2, we know block 2 has a mass of 5 kilograms. So if I'm just looking solely at block 2, we know that it's also going to have an FW, which is going to act straight down. And again, FW is m times g, so 5 times 10 is going to give me a weight for block 2 of 50 newtons. But now when I calculate the normal force, I have to keep in mind that I also had block number 1, which was sitting on top of that. That block number 1 is going to put an additional force downward onto block 2. So the normal force is still going to act perpendicular to that contact surface. We're still going to have that 90-degree angle, but this time I have to not only consider the weight of block 2, but also that 10 newtons of weight coming from block 1. So overall, the normal force for block number 2 is going to be 10 plus 50, or 60 newtons total. So when we start looking at systems, we're going to learn two things. The first of which is that entire systems can be treated as one single object, and we can therefore analyze the forces acting on that object. So if you forget that there were two separate blocks here and just treat it as a single block, we would have a total mass of 6 kilograms, right? 1 plus 5. So if I look at this thing as a whole single unit, okay, those forces that would be acting on it are called external forces or outside forces because they're acting on the system as a whole. So if I look at the system as a whole, it has a total mass of 6 kilograms and therefore a total FW of 60 newtons and therefore a total normal force of 60 newtons as well. Okay? And these would each be considered external or outside forces. We can also look at systems by looking at each object individually, and that's how we started to do the warm-up activity. So again, if you look at the forces acting on just block 1, we know it's going to have an FW which is 10 newtons, right? Because remember, Fw is mass times gravity, so 1 times 10, and it will have that normal force of 10 newtons as well. Okay. All right, so that force pair that we just drew acting on block number 1, the normal force in particular, is done by block 2. That is an internal force. It's done by an object within the system on another object in that system. We can also look at block number 2 individually. Remember, block 2 has a mass of 5 kilograms. So we know that if we look at just the weight of block number 2, okay, Fw is mg again, so we know that just the weight of block 2 would be 50 newtons. However, notice that block 1 is also acting downward on block 2. So there's another Fw here from block 1, and we'll call it 1 and 2, of 10 newtons. That force of block 1 acting downward on block 2 is also an internal force pair, because it's caused by an object within the system on a second object of that system. And when we add those two together, that's how we get the total normal force on block 2 of the 10 plus 50 for a total of 60 newtons. So something to keep in mind with internal forces, we know they're done by one object of the system onto another object of the system, and because of that, they cannot create a net force. So remember from last chapter, if net force is equal to 0, we know that that system is not accelerating. It's either at rest or it's moving at a constant speed. So internal forces, again, that we saw on that warm-up problem, we know block number 1 was acting downward onto block number 2. Block number 2 was also acting upward onto block number 1. Okay. Neither one of those forces caused that system to accelerate. This also works for systems where you have objects stacked side by side like we see here. We have 3 boxes or blocks, each with different masses, and this time we have 2 forces, force A and force B, being applied to the system. Notice force A and B are both equal to 50 newtons and they're going in opposite directions. So what we're going to do first is think about the system as one object, okay? And then by looking at it as one object, that's going to allow us to determine what those external forces are. And so if I just drew this as a single object, okay, the external forces are easy to see. We've got an external force here of 50 newtons, and we have an external force here of 50 newtons. Now, overall, the acceleration of that system, because we have equal forces in opposite directions, we know we would subtract them. 50 minus 50 is going to give us an acceleration or an overall net force of 0, and so this system is actually not even going to move. Okay. If we look at each object individually and label the forces acting on it, we're going to start over here with force A. We know force A is pushing on block number 1. That's going to cause block number 1 to push on block number 2. Okay. Block number 2 is going to provide a contact surface for block 1, and it's going to cause a force that goes back in the opposite direction. And so this would be an internal force pair. Another force pair that we see is block 3 is being pushed on to the left by this 50 Newton external force, which is going to cause a push on block 2. Block 2 is going to provide a contact surface for block 3 and therefore push back as well. And this yellow set of arrows here represents another internal force pair. Okay. Now, one thing that we can tell from these force pairs, because our overall F net of this system is 0, because we've got, again, 50 newtons coming from each direction, what that tells us is that the value of every single one of these internal forces is equal. So they're all 50 newtons as well. Okay. And that's going to change a little bit when we get into our next couple lessons. But for right now, if your external forces are equal and in opposite directions, that means your internal force pairs within that system are going to be equal to that magnitude as well.